For those of you who don't know me, my name is Evelyn Gates. I'm a cosmologist and a trustee here at the Center for Physics. If you have any questions during the coffee hour, don't hesitate to ask me if you're new to the center, and if you are, welcome. I'm especially delighted to introduce today's colloquium speaker. Had the privilege of sharing an office with him for the past week, and in addition to great physics talks, we had everything ranging from classical music to politics and sort of all the good things that you usually get when you meet someone new. So today's speaker is Fakhri Zahedy. He was an undergraduate at MIT. I did his PhD work at the University of Chicago with Xiao Chen. Spent 4 years, I think, at Carnegie Observatories before moving to the University of North Texas this past January. His talk today, which is entitled Physics and Chemistry of the Baryon Cycle, Unraveling the Complex Interplay Between Galaxies and Their Gaseous Environments, is going to highlight some of the science of the current workshop on the circumgalactic medium. And I've been very impressed with what I've been hearing in various places about this workshop. Galaxy formation and evolution is still one of the anchors for understanding the overall evolution and structure of the universe. And the physics involved is fascinating. It's the large scale, small scale connections. There are feedback, mixing processes you have to understand. And the CGM offers this really unique arena in which to explore this stuff. So basically, we've got a really complex system with some really hard questions and very difficult to wrangle some of the details. Yet the payout is going to be some really great insights and some results that are going to help form our future understanding. So for a physicist, difficult, big payout, it doesn't get any better than that. So I'm really looking forward to this talk. We will have time for questions. Please, as usual, those that are members of the CGM workshop, hold your questions till the end to make sure that we give a chance to participants from the other workshops to ask their questions first. Okay, so with that, I would like to welcome Fakhri to the stage.
All right. Can everybody hear me? Okay, I'm loud, so I'm always audible even without amplification. Well, thanks again. It's been a great 2 weeks, and I've had a blast here talking and meeting and just discussing science with you all. Since this is probably the last time this summer that we are all in this room together, I would like to invite you all to rise in appreciation of the people, the staff especially, who made everything possible. I think it's so much work to organize something like this, and I think it's been wonderful what they have done for all of us, so we need to worry about science and nothing else. All right, thank you. Okay, so here's our game plan. I'll start with some introduction, like let's motivate why you and me should care about any of this galactic science, and then we'll go into 3 different parts: some physics, some chemistry, and then some vision for the future. So I would like to start with this, which is a timeline, a simplified timeline of our universe from the Big Bang to the present day, almost 14 billion years later. Every one of us here today, astronomers or not, actually work to understand one or more parts of this timeline. The first 3 minutes are important for understanding the Baryon asymmetry, why there is more matter than antimatter, why the cast of particles in the second model is the way they are. By the end of the first few minutes, the universe basically ends up with almost all the hydrogen and helium that we have today. Now, people like me in this workshop, we care about the rest, all the other 13 plus billion years. So objects like stars and galaxies are born, and they grow and change. The rest of the periodic table is populated. So one additional note, you will hear me refer to redshifts again and again throughout this talk. This refers to cosmological redshift, which you can think of as a nonlinear proxy for distance and look-back time in the astronomical pounds, and as you can see from this diagram. So I would like to start with a bit of history, actually. Just that development of spectroscopy really changed everything for astrophysics. A lot of people like me, I'm a spectroscopist, so I'm a little biased, but I consider the arrival of spectroscopy to be the birth of astrophysics, at least beyond the solar system. I would like to also remind you that spectroscopy was actually first used to identify elements, chemical elements in stars. So it's also astrochemistry. So back in 1850s in Heidelberg, Kirchhoff and Bunsen experimented with this newly invented instrument called the spectroscope. And they heated various salts and gases and found that each produced a unique emission spectrum. So these gentlemen wrote about what they found. They recognized that this actually had great potential for identifying what the stars were made of. So within about a decade, Kirchhoff had identified more than 10 elements among the hundreds of lines that he saw in our sun's spectrum. And by the end of the century, more than 10,000 stars had been observed and grouped into the various spectral types. And we have come such a long way today. All right, so this is the silly version of the astrophysics periodic table of elements. And by the way, this is our first yellow good to know box. And throughout my talk, we'll encounter more of these boxes. And they will provide context, especially for those of you who don't work in my field, so you have a bit of basic understanding on some of the more difficult jargon. So yeah, for us astrophysicists, metals include carbon, it includes wood, it includes oxygen. Anything with atomic number greater than 2, that's metal or heavy elements. So, all right, let's try again and be serious now. So this is our version of the periodic table with every element labeled by what we think is their most dominant production channel. So we have the Big Bang itself, or hydrogen and helium, different types of supernova explosions, merging neutron stars, Wilma stars dying, etc. You can see that, again, the Big Bang produced most of the hydrogen and helium, but everything else here, every atom in your computer, every equipment you use in your lab, it was all made by stars, or by stellar deaths, or remnants of stars after their deaths. And this is one of the very, very tangible way that astrophysics actually directly in touch with our world today. But what does this have anything to do with galaxies? I'm getting there. I want to first show you two complementary pictures. Comparison of how our universe looks like in theory and in observations today. So on the left, you're seeing large-scale distribution of dark matter in cosmological simulations. This is a large patch of simulated universe with its largest scales, about 1 gigaparsec on the side. And again, 1 parsec is its grid unit, roughly a little over 3 light years. So on the right, this is the large-scale distribution of galaxies from the Sloan Detailed Skyscraper Survey from earlier in the century. Now, to me personally, this is one of the greatest triumphs of modern science. The fact that we are able to draw a connection between the observed large-scale distribution of matter on the right, on the left, on the right, sorry, with the primordial distribution of matter, dark matter, seeded all of this, predicted in theory. So on this large scale, gravity is basically the only force that you need to care about. And in this physical picture, dark matter dominates the gravitational potential, roughly 6-1, and provide the scaffolding, the skeleton around which structures and galaxies can reside and grow over time. We call these structures in astronomy and cosmology, once they have collapsed, dark matter halos. Most importantly, you see how simple our universe is on the large scale. You see the manifestation of the so-called cosmological principle that our universe is homogeneous and isotropic. You can see here, that's a dark matter halo for a massive galaxy cluster, and there is a massive galaxy cluster. Sorry, I am not supposed to pass that line. Forgot about it. Sorry, Emily. All right, so that's the large scale picture. Once you move to the smaller scale, scales of individual galaxies, a very different picture emerges. This is a small portion, the very famous Hubble Ultra Deep Field, basically what happens if you use the Hubble Space Telescope and stare at a seemingly empty patch of sky for 2 weeks. So this picture is the exact opposite of homogeneous and isotropic, because now you see a huge diversity and complexity of galaxies of all types, shapes, and sizes. Now, if you boil down the study of galaxy evolution to its essence, it's all about understanding how and why the universe ends up with a huge diversity of galaxies after almost 14 billion years. And we know that the universe started simple, it still is simple on its largest scale. So then, how can so much diversity emerge from this relatively simple beginning? And I just love this quote. This is really the last sentence from Darwin's On the Origin of Species. I first read as a high school student. It's in the public domain. If you haven't read it and you have a long flight home, download it and you won't regret it. It's an amazing book. Okay, so we can then ask, what is the essence of a galaxy? Someone like me, galaxies are in the business of forming new stars. That's it. That's top of the list, job description for a galaxy. I'm showing you here a color image of the nearby galaxy M51, about 20-something million light years away, 7 megaparsec, taken actually last week by us during our outreach night, Astronomy on Tap, here in town. Myself and some of my colleagues here, which some of you may recognize. So that's a tiny telescope, only about 4-inch across, with a modern CCD camera, but already you can see the spiral structures. It's quite amazing. But this is a much better view. This is actually the Hubble Space Telescope. You guys have the LHC, we have Hubble and JWST, and this is why. This is why it costs so many billions. So much more detail here. And when I look at this, a number of things jump out at me. Let me make this clear. There. So I've now circled regions around the spiral arms of these galaxies where a lot of star formation is happening. We call them H2 or ionized hydrogen regions because there's a lot of emission from ionized hydrogen gas, which has been ionized by blue young stars recently born. It's red, as you can see, because the dominant emission line is hydrogen alpha, 6564 angstrom. And on top of that, you see bright blue light coming from massive young stars embedded within these clusters. So that's a galaxy. We have been studying galaxies for 100 years now, roughly speaking. One of the big problems that remains today is this. A couple of decades ago, people started comparing the theoretical distribution of dark matter halo masses, the observed mass distribution of galaxies, using the known cosmic mass ratio of baryon to dark matter, which is about 1:6. You can plot the expected galaxy mass distribution given that ratio, and that's the red dash curve here. Well, it's the observed mass distribution of galaxies. It looks very different, doesn't it? What are we seeing here? 3 things. One, you see too few massive galaxies on the high mass end. You also see too few low mass galaxies. And all across, you see too few galaxies across the board. Galaxies simply look like they haven't been converting most of their baryons into stars. And here's another version of the same plot. The figure shows the fraction of a galaxy's halo's cosmological budget of baryons, which it has converted to stars, plotted against the mass of its dark matter parent halo. You can see here that Milky Way-like galaxies right here at about 10 to the 12 solar mass of halo mass, it's converted only about 20% of their budget baryons into stars. Dwarf galaxies on the lower mass end and massive elliptical galaxies on the high mass ends have done far, far worse. Less than 5 to 10% converted into stars. So all across the wide range of masses, it looks like galaxies, the so-called star formation factories, are really bad at their job. But the most important thing to note here is that galaxies seem to be bad at forming stars differently at different masses. Some are doing worse than others. So these actually lead to a couple of broad questions that motivate me and my colleagues here. Number one, where are the rest of baryons if they're not locked in stars? And number two, what are some of the physical mechanisms responsible for suppressing star formation in galaxies across different masses? So let's address the first question. Where are the baryons? Well, if the bulk of the baryons are not in stars, they have to be in a lower density gas phase somewhere. So this is an optical image, visible light image of the nearby spiral galaxy M81 and its major satellite galaxies. Looking at this looks like a bunch of galaxies each doing their own thing, not related to one another. you see a very different picture in a map of 21 centimeter emission, the same system. By the way, this is an emission from the hyperfine splitting of the ground state of the hydrogen atom. So if you see this, you see a lot of hydrogen gas. So but you're now looking at different processes of the baryon cycle in action. This exchange of gas between galaxies and their surroundings. Galaxies can accrete gas in intergalactic space, replenishing their supply of gas to form stars. And then star formation can drive powerful winds that expel matter and heavy elements away from galaxies, enriching the intergalactic space and the environment around them. Galaxies can interact with each other by gravity, stripping gas from one another, like you see here. So a lot of these complex interactions take place in the gaseous halos of gas we call the circumgalactic medium. For that reason, this medium, like Evelyn mentioned, is really a great place to investigate and look for how these different baryonic processes, these gas processes, regulate star formation over time. And in a nutshell, that's what our 3-week workshop has been about. This is a really nice chart summarizing how the movements of baryons in and out of galaxies are intertwined with galaxy evolution itself. Again, I will assert now, and I hope that I will convince you by the end of this hour, that understanding the physics and the chemistry that drives this baryon cycle is critical to the completion of our understanding of galaxy evolution. Now, for the longest time, people have been studying galaxies by looking at what they do, how they form stars, their internal structures, their dynamics, etc. But the folks here, we study galaxies from a more resource and goods-oriented angle. The resource I'm speaking of course, is gas, the fuel that a galaxy needs to its job as a star formation factory. And the goods, of course, are what's produced, and the elements produced by those stars. So when I talk to people outside of my field, I often tell them that I'm an economist of galaxies. There's so much of what people like me work on is about understanding the physics and chemistry behind the process of the baryon cycle and how that impacts galaxy evolution. Of course, there's a big difference. In real economics, the hidden driver of everything is human psychology and behavior. But with the baryon cycle and galaxy evolution, it's physics and chemistry. So I hope to highlight some of that with the rest of our time here. Now, beyond the closest of galaxies, detecting this CGM in emission is extremely difficult. Why? Because you hit by a combination of the low density of the gas and also the cosmological dimming, which scales as the Nordic power of redshift. Instead, it's much easier to detect the gas in absorption. The way this works, you point your telescope at a bright background source, like a quasar. And by the way, that's another good to know box. And because of that, the gas passes through structure in the circumgalactic medium of a galaxy in the foreground. You are going to see absorption lines imprinted on the spectrum of the quasar by that foreground gas, and you can see that on your data. It is from studying these profiles that you can learn a lot about the physical properties of the gas. The line of sight velocity will tell you its movement relative to the rest frame of the galaxy. The depth of the line tells you basically a count of how many atoms you're seeing. Width tells you something about the temperature, turbulence possibly present in the gas. And then the relative amounts of one element to another, which will become important later, tell you something about the chemical composition and the ionization state of the gas. This is really my bread and butter, our bread and butter in this workshop. I hope this is clear to you conceptually, because if not, nothing is going to make sense. Now, using this technique, we can look at different absorption species, different types of lines from different elements present in the CGM. And each of these probes different gas phases, gas densities, temperatures, and so on in the CGM. So this figure shows how these various ions, weird names, right, that we detect in the CGM correspond to different regimes in the phase temperature and phase and density phase space. You have low ionization gas like oxygen 2, singly ionized oxygen, or magnesium 2, singly ionized magnesium, facing cool gas at 10 to the 4 Kelvin. You see intermediate ion, slightly more highly ionized gas at about 10 to the 5 Kelvin. And then you also have on top this really high coronal high energy lines that we typically see in X-ray observations, representing gas at temperatures of about 1,000,000 Kelvin or so. Now, if a galaxy is massive enough, like our Milky Way, or even more massive than the Milky Way, you can expect all of these phases to coexist somehow in this CGM. This is a cartoon picture showing what the phase structure might be like in the CGM, with a low density, volume filling hot phase, and embedded within them are lower temperature gas clouds, smaller from the warm and the cool phases. Okay, so how does absorption line study work in practice? Because you have to rely on background distant quasars. Most of the time, you can only find one background line of sight piercing the CGM in a foreground galaxy. If you want to get a nice sample, you have to be a bit clever about it. Say you want to study galaxies of a certain mass, like something like our Milky Way, but a little back in time, 8 years ago, a redshift of 1. You first have to find a sample of them, which, by the way, is not that easy to do. Galaxy survey is very difficult to do and time-consuming. And you have to find those galaxies that are probed by background quasar at some distances, right? And then you obtain spectra of that quasar and do the whole absorption search and analysis that I alluded to earlier. Then you make the assumption that all these galaxies are essentially different instances of a representative model galaxy of that mass. And if this assumption holds true, then your survey is basically equivalent to studying the CGM of this model galaxy 6 different ways, actually 6 different distances. And then you can infer the average properties of the CGM for this population based on this ensemble average approach. So that's how it works. Right. So once every decade, these countries' astronomers get together to discuss what science the community needs to prioritize over the coming decade. It's called the decadal survey. Now, after each survey, a report with a set of recommendations is issued to policymakers. I believe there is also one in particle science, right? But yeah, astronomy just had one just a couple of years ago. The latest report indicated 3 major scientific priorities, one of which is the physics of galaxy evolution. And it has something big to say about CGM science, which I reproduce here. So there is now a broad consensus that the CGM is key for unlocking some of the secrets of galaxy evolution. But the report also states that we need to do more to understand it. We need to know a lot more about the CGM than simply to say, oh, it's there, and it's always there. And to do that, we need to understand the underlying physics and the chemistry that are at play. So that was the end of my introduction. Now let's talk about some physics. Physics is an extremely broad topic, of course, so given the time constraints, I'm only going to limit myself to addressing just one question, which is, how do we prevent star formation in massive galaxies? To motivate this part, a really interesting question one can ask is, what is the relationship between the intrinsic properties of galaxy and its CGM? How does the CGM change as galaxies themselves change over time? We have known for a while that star-forming galaxies have tons of cool gas in their CGM, like in this picture here I showed earlier. And this abundance of cool gas is likely what's sustaining their ability to keep forming stars over billions of years. We can now contrast this picture in spiral galaxies with what we see in massive quiescent or elliptical galaxies. These are massive galaxies, often multiple times more massive than our own Milky Way. The most important characteristic is that they have not been forming stars for billions of years. They look different. Right? Instead of grand spiral arms, you see boring blobs of elliptical-looking block stuff, right? And it's just not so exciting to look at. From X-ray observations of hot gas, we know these galaxies are surrounded by massive amounts of hot halo gas. But what about the cool CGM? It's the one that's relevant for potentially forming stars in the future. This is actually a rather important point, because most existing CGM studies have been focused on star-forming galaxies, and that makes sense. They look interesting, it makes sense that you want to look at them first. But I think it's equally important to also look at the CGM of massive quiescent galaxies. What happens to it as galaxies themselves stop forming stars? Are they out of cool gas? Or perhaps there is some physical mechanism acting on it after they are retired from star formation to make it impossible to resume star formation? Can we look for clues from their CGM? So this was actually the main motivation for an observational survey I led a few years ago called COS-LRG, which I would like to highlight now. We had a sample of 16 massive elliptical galaxies, each with a stellar mass of more than 100 billion solar masses, so it's at least 2 or 3 times more massive than our Milky Way. And each is probed by a background quasar at about less than 160 kiloparsec, roughly a third of the radius of the parent dark matter halos. My collaborators and I, we used the cosmic origin spectrograph, a fancy instrument on the Hubble Space Telescope, a UV-sensitive spectrograph at that, to search for and constrain the bulk of gas in their circumgalactic medium. Now, because hydrogen forms the bulk of any gas, understanding the hydrogen content is essential if you want to unravel their physical properties. And this is why going to space and getting UV coverage is necessary, because these lines can only be detected in the UV wavelengths at the distances these galaxies are at. So you have to go to space. No other alternative there. Now, this diagram illustrates the locations of the 16 lines of sight relative to this ensemble galaxy in the center. And so here's the global overview of what we found. Despite the fact that these galaxies have not been forming stars for at least a few gigayears, we still detect the presence of cool gas in a large majority, 80% of them. So it looks like there's still abundant cool gas around these retired galaxies. How much? Well, our estimate is that the typical massive elliptical galaxy is surrounded by a few tens of billions of solar masses of cool gas in their circumgalactic medium. And I will tell you, this is a surprisingly large amount, because it's actually comparable to the estimated total mass in the cool CGM of star-forming galaxies. So these retired galaxies actually contain as much gas in their CGM as star-forming galaxies. And it was a surprise to us. So we didn't expect that at all. It would be like equal to finding that there's a population of retirees in Florida who are like rich, but somehow are not spending their money. You have to figure out why. What is in the underlying psychology that's causing them to just like hoard their money and not do anything? That's kind of the kind of puzzle that we had to deal with here. So what we did next, well, we examined the way these clouds are moving. So here's what happens when we plot a histogram of the line of sight velocity of these clouds in the CGM, and that's shown in red here, dotted red histogram. And what's intriguing is that the velocity distribution of the cool gas is actually quite narrow. It has a width which is only about half what you would expect from their gravitational potential well, given their mass. Basically, they're moving way too slowly given their expected orbit. But even more interesting is the fact that we don't see this in the CGM of lower mass star-forming galaxies, which is shown in gray here. Instead, it looks like their velocity distribution is entirely consistent with the kind of kinematics that you would expect given their gravitational potential. So this is actually a very robust measurement, and it has since been independently confirmed by at least 2 or 3 different groups. Now, the observed low velocities of cool CGM clouds around these massive retired galaxies are consistent with 2 things. One, that the cool clouds is experiencing some sort of hydrodynamical drag as exerted by the hot halo surrounding these galaxies as they're orbiting and going about their business moving around. And eventually they reach some sort of terminal velocity that is lower than the expected orbital motion. Now, drag is, of course, a dissipative interaction, so energy will be lost. Because of that, the clouds are going to be losing energy over time, and it's going to slowly fall and spiral into the galaxy. And as it does that, it's going to be slowly destroyed, most likely never reaching the galaxy, because if it does, then there should be a lot of star formation around these galaxies. So this can potentially explain why, despite having so much cool gas just hanging around on a 100 kiloparsec scale around these galaxies can somehow maintain the quiescence over long time scales. Because most of the clouds around it will never survive long enough to cool, condense in fall, and make new baby stars. All right, and one last piece of evidence I would like to discuss is the thermal properties of the gas. Like I mentioned in my introduction, the observed line width of these absorption lines in the CGM encodes critical information about the line broadening mechanism. Absorption line is not going to be infinitely thin because your atoms or ions are not at rest. There are 2 main mechanisms that contribute to the observed line width. One is the kinetic temperature of the gas, just random motions, right? Random kinetic energy of the atoms. And the other is just some general generic non-thermal sources. This can be bulk motion or turbulent within a gas cloud. As you can see, this equation has two unknowns, the temperature and the non-thermal broadening, meaning that for a gas cloud, we can figure out the gas temperature, the non-thermal broadening, by comparing the line widths of at least two different species of different mass. Let's show here in this example from the work of my collaborators. As the first example on the left is a limiting case where the thermal broadening is dominant. So the second term is basically gone. And in that case, the observed line width is going to be proportional to inverse square root of the mass of the atom. Second example is a case of the reverse where the turbulent is actually dominant, the non-thermal broadening is dominant, and here the line width is going to be independent of the mass of the atom. This is hydrogen and silicon, very different, and sulfur, very different masses, 32-fold different. Okay, so now this is what it looks like when we plot the cumulative distribution function, the fraction of thermal total energy density, that is thermal plus non-thermal motions for the clouds, because it's a ratio of the square of the thermal versus non-thermal broadening line widths. And I'm showing you here the data in red for the massive ellipticals and in blue for normal star-forming galaxies. Okay, so what are we looking at here? You can see here that on average, CGM clouds around massive elliptical galaxies have a higher degree of non-thermal contribution to the internal energy when compared to star-forming galaxies. So these clouds are in a way more turbulent internally. So we have found here an observable distinction, a clear difference in the CGM of passive galaxies or elliptical galaxies versus normal star-forming galaxies. So while the amount of cool gas in the CGM is roughly the same in both types of galaxies, not only do these clouds move differently in different types of galaxies, but internally they're also different. That's the point I want to emphasize here. Okay, so at this point, I want to pause and recap what we have learned so far in our quest to answer this question. So by studying the CGM of massive elliptical galaxies, we have found that there is just about as much cool gas there as in the CGM of normal star-forming galaxies. There are observable differences. First, the clouds appear to be moving internally slowly, more slowly than those around star-forming galaxies. And these clouds also appear to be internally more turbulent too. It appears that perhaps hydrodynamic interactions between cold clouds and the volume-filling hot phase of the CGM may be responsible for preventing these clouds, which are formed at large distances, from retreating onto these galaxies. All right, so I would like to switch gears now a little bit and start talking about chemistry, which is near and dear to my heart. We will first look into why chemistry provides the physical link between galaxies and their gas. And then I want to show you what we have learned from my work and those of others about the CGM chemistry and why we can use it as a way to basically fingerprint the gas and then link it back to its physical origin in different individual galaxies. Chemistry is central to the Baryon cycle because it's basically about the problem of how do you transport heavy elements out of galaxies and also onto galaxies. I want to show you this picture from simulated star-forming galaxies like our Milky Way from the elusive 2NG suite of simulations. This is work led by Selin Peru, who's here at the conference workshop. And this is at a redshift of about 0.5 or about 5 billion years ago. And you can see the extended disk of the galaxy here, aligned with the middle part of the picture, oriented along the major axis of the galaxy. And the color here corresponds to gas metallicity, defined right here. It's a logarithmic quantity. So brighter means more metal-rich, more heavy elements. You can see metal-rich outflowing gas winds flowing out of these galaxies, proceeding primarily along the polar axis of the galaxies because there's a disk. It's the path of the least resistance. You can also see in reverse that lower metallicity in falling gas prefers to proceed mostly along the major axis of the galaxy. So basically, if you were to plot metallicity as a function of angle from this major axis, you would expect something that looks like this. Metal-rich outflow flowing close to the minor axis, metal-poor inflow proceeding primarily along the major axis. That's the theory. Now, over the past few years, many people have been searching for this kind of signal in the CGM. The dependence in metallicity with distance orientation, mixed results, I would say. I think this is a fair representation of the kind of data we've seen. This is the most recent investigation led by Samir and Jane Charlton, who are here in the audience, based on almost 50 galaxies. Each point here represent a metallicity estimate for a single thematic cloud detected in the CGM of a given galaxy. And sometimes you find multiple clouds in a single galaxy. Samir finds there's a large number of discrete clouds close to the major or minor axis, so perhaps indicating there is more cool gas there. If you talk about the metal, at the same time, he doesn't see any trend in gas metallicity in the CGM as a function of angle from the major or minor axis, basically a scatter plot. Likewise, myself and collaborators, we find that there is no obvious trend in gas density with distance from galaxy in the CGM either. So what this tells us again, I think, is that the CGM is complex and you simplify it at your own peril, basically. Each line of sight through the halo, the CGM likely intersects multiple gas structures, each having its own distinct origins. And then those gases can mix and mingle, and by doing so, changing their metallicity in the process. So if you just look at the absolute metallicity alone, it's not enough. That's why now I want to go back to this periodic table. Once again, this is the periodic table with each element labeled by the fractional contributions from different channels, processes into the production of these elements. We recognize that A, these different channels operate on different timescales, and B, they also often prefer different populations or locations within a galaxy. And this is why studying the detailed chemical composition can be very fruitful. Because, in fact, the relative abundances of different elements give us an archaeological record of CGM enrichment and also its sources, basically where the gas is coming from. And these are some of the elements that we see in our absorption type studies, the common elements that we see. So most relevant to our upcoming discussion is to realize that there are two main types of supernova explosions, and they have very different chemical output. One is called type 1 supernova, which is caused by a white dwarf star or a pair of white dwarf stars that exceed the Chandrasekhar mass limit, about 1.4 solar masses. This explosion is common in old and evolved stellar population, and what we know about them is that they produce a heck of a lot of iron. About half of the progenitor mass ends up being expelled in iron, so about 0.7 solar masses of gas just expelled as iron nuclei. The other is called a core collapse supernova. So these are produced primarily in massive stars of 10 solar masses or higher. These stars don't live long. You can normally expect this supernova to occur only in young stellar populations. We think that they produce a high majority of the so-called alpha capture elements, which include things like neon, magnesium, oxygen, and silicon. If you may realize that the masses are basically multiples of 4 atomic masses, which is the mass of a helium nucleus. Now, relative abundance measurements have actually been performed for ages, decades, by stellar astronomers on stars in our own Milky Way. These are relatively recent results from the Sloan Still Sky Survey, showing how the relative abundance of alpha elements, like magnesium, or iron, varies for stars in the disk and also above the disk of our Milky Way galaxy. Diagrams like this has helped better understand the assembly history of the Milky Way because it tells you something about the timescale of the formation of these components. It tells us something about the star formation timescales of different parts of a galaxy, also the mass assembly of different components like the bulge, disk, the halo of the galaxy, and how it unfolded it over time. Now, in quasi-absorption line studies, this detailed abundance analysis remained for the longest time the purview of those studying damp blind alpha absorbers. That's another box there. It's basically patches of neutral gas detected, possibly probing the outskirts of interstellar gas of distant or high redshift galaxies. That's all you need to know. There's been plenty of chemical studies on DLAs over the past 3 decades, and here's an important and seminal work investigating the chemical enrichment history of high redshift DLAs done by Liminlu and Paul Sargent at Caltech in the early 90s. This plot shows the observed elemental abundance ratios of different elements relative to iron, plotted as a function of metallicity here. The most obvious thing that you can note is that these DLAs show a predominantly alpha-enhanced chemical abundance pattern relative to our sun. Silicon, for example, an alpha element, is overabundant compared to iron. It's about 0. These authors concluded that at these high redshifts, these early parts of our universe, there simply hasn't been enough time for type 1 supernova to go off in large quantities and to really enrich this medium with a lot of iron. That's TLAs. Well, in the same spirit, what myself and collaborators have done is to investigate the chemical makeup of the CGM and how it varies with star formation properties of the galaxy. In the work I'm showing you here, we've looked into the radial profile of the mean observed iron to magnesium ratio, or iron to alpha, the function of distance in the CGM. So the blue points here are measurements for star-forming galaxies, probably Milky Way-like. The red points are elliptical galaxies at the same epoch. So there are two interesting things to note here. First, in general, the iron to alpha or iron to magnesium ratio values are higher around elliptical galaxies when compared to star-forming galaxies. And second, the iron to alpha ratio in the CGM of elliptical galaxies appear to decline with increasing distance from the galaxy. What that tells us is that a few tens of kiloparsec away from these massive elliptical galaxies, type 1a supernovae have contributed significantly to the chemical enrichment. On the other hand, far from galaxies, CGM is richer in alpha elements, which indicates a more primitive, a far earlier enrichment epoch dominated by core collapse supernova, massive stars. This is consistent with the gas originating at large distances from intergalactic space beyond the circumgalactic medium, accretion. Of course, the CGM, like I mentioned, is a lot more than just the cold phase that we see in the absorption spectrum. I'm showing you now, here in magenta, the range of measured iron to alpha ratio from the X-ray emitting phase, the 10 to the 6 Kelvin gas or hotter in the CGM of local elliptical galaxies. Interesting thing to note here is that it's consistent with what people like me have measured in the cool 10 to the 4 Kelvin phase, both the mean value as well as the range, the spread. Now, the reason I want to show this is there's still debate among astronomers about the origin of gas, especially cool gas, in elliptical galaxies. Is it coming from stellar mass loss? Is it coming from condensation or precipitation from the hot CGM? Now, at least from this line of evidence, we can infer, based on the sheer similarity, chemical composition, that we see perhaps a causal connection between the hot and the cool gas, that condensation or precipitation from the hot atmosphere is a significant source of cool gas, at least within a few tens of kiloparsec or so from these galaxies. Now, what you have seen so far pertains to galaxy populations or means or averages, general trends. But as is often the case with the universe, this gets complicated when you look at individual galaxies. Now, I want to show you this very intriguing case of cool gas at only a few kiloparsec away from a massive elliptical galaxy. Once again, this is a high-mass galaxy with no detectable star formation whatsoever. I've been studying the systems for years, from the ground, from space, and with everything I could get my hands on. Now, we know that it does show plenty of gas with basically near DLA, high H1 column density, detectable across both lines of sight here, A and B, only 3 kiloparsec away from the galaxy. So there's a lot of neutral gas there, which is, of course, a little puzzling. We also know the gas is primarily iron-rich. Again, you see here the iron to magnesium ratio around these galaxies, or these different clouds that we detected along these two lines of sight, right, the red and the blue, A and B, as a function of velocity from the rest frame of the galaxy. But if you look a little closer, you see that while the gas is primarily iron-rich, there are a small number of detectable components like these two here that appear to be more alpha-enhanced. You can also see there's a fuzzy-looking tiny object here, right? Like, what is that? Only a few kiloparsec away from this B line of sight. So these have been bugging me for a long time. I tried to get a spectrum of this object every time I could, but it was almost impossible because this B line of sight is so bright and it's so close to it in angular separation, and because of our atmosphere, it's just impossible. More than 100 times brighter. But a couple of years ago, we caught a break. So a couple of years ago, I took Ben Snyder, brilliant undergraduate student, to work with me here then at Carnegie when I was a postdoc. He was then an undergraduate at Cal Poly Pomona. Now he's in second year of PhD at UC Santa Barbara. I assigned Ben to study on a project to study the galaxy environment around ANSYS, and how this environment affects what we see in the CGM. So Ben basically did a galaxy survey of a dozen fields, including, it turns out, the field around this massive galaxy. So he found that there are two neighboring galaxies at some distance from this massive galaxy. One is more than 200 kiloparsec away, and it's like a galaxy with like our Milky Way, with a mix of emission and absorption spectrum. What that tells you is there's some underlying star formation with a mature star population. But the closer one, G1 here, that's the blob I was talking about earlier. That's the one that I was most interested about. This galaxy, based on our image analysis, is a dwarf, similar in mass to the Large Magellanic Cloud, the satellite of our Milky Way, in mass and in luminosity. It's a disky, it's strongly star forming, and it, again, because it's star forming, it has a very young star population. You see that in the blue spectrum there. So here's where it gets interesting. When you plot the location of G1, that galaxy, that blob, onto this iron to magnesium ratio plot that you saw earlier, we found out this is where G1 is kinematically. There's a strong kinematic and close, also spatial correspondence between where G1 is and where the highly alpha element enhanced gas that we see is. So the alpha rich component that you want to focus here is the blue one here, which means it's from the B line of sight, which is closer to the G1 galaxy projection. So when my student showed me this, I got really excited. I was like, wow, amazing. So what I did next is to look into the literature to get some clues. So we obtained important insight from emission line mapping, the CGM. This is a study led by Sean Johnson, Michigan, that is particularly relevant. In one of his papers, Sean mapped both the galaxy environment and extended emission nebula around a radio-loud quasar. You can see on the left, all the galaxies he had identified around that quasar, which here is at the center of this image. And on the right, the velocity map of this extended gas emission. The circles mark the location of the quasar's neighbor galaxies, again on the same color scheme as the gas. And just like in my elliptical galaxies, here you too can see strong kinematic and spatial correspondence between the nebula emission and the location of the nearest galaxy. For the most part, the gas has very similar velocities to the galaxy nearest to it. They're almost the same colors on this map. So his conclusion is that this suggests an origin of the gas from stripping of interstellar gas of those galaxies, the course of galaxy-galaxy interactions with the host galaxy of the quasar, which is the dominant galaxy in this system. So based on that, I can now draw the following conclusions. Most of the gas that we see at only a few kiloparsec away from this massive LRG has been highly enriched by type 1 supernova within the galaxy. But the presence of alpha element enhanced components and the close kinematic and spatial correspondences to the star-forming satellite galaxy suggests a physical origin from recently stripped CGM gas. On this, I should mention recent work done by Annalisa De Chia in Europe showing that the interstellar medium to Large Magellanic Clouds is alpha enriched. Again, at a level within uncertainties that is consistent with the value we found for the alpha-rich gas near the lens, this elliptical galaxy. The reason I wanted to spend some time on this is to illustrate that yes, with high completeness galaxy survey, knowing all the galaxies in your field, and also high quality absorption spectra from the CGM, we can figuratively take chemical fingerprints of gas that we see and then directly tie it back to certain individual galaxies that we see in the field. So at this time, I want to give shout out to my collaborators here from the CUPS team. CUPS is a collaboration centered on two large Hubble Space Telescope programs to study the CGM at intermediate redshifts between 3 and 8 billion years ago. They're looking at 15 UV bright quasars in the sky. And to accompany the quasar data, we've been spending more than 5, 6, 7, I don't know, Gwen, how many years, 8 years maybe, performing an ambitious, deep, and high completeness survey with multiple weeks of observing time. Magellan, which is in Chile, and also ESO, the European Southern Observatory Telescopes in Chile. I want to make sure to give a plug for CUBS because so far 4 of our publications have some emphasis on circumgalactic chemistry. Had 2 on neutral gas led by Erin Betcher, who is here. We had another one by ionized gas led by Tom Cooper, formerly of Carnegie, and one led by myself. I kind of want to highlight next. I want to show you an example of things we've learned in this survey. This one is from a study I led, looking at chemical abundance in optically thick gas in the CGM, what we call Lyman limit systems. Okay, it's not that important. But for the sake of this example, I want to focus on how nitrogen to alpha ratios vary with gas metallicity. Before I show you measurements, let me show you this. It's a great point to show you measurements of gas abundances and ratios in the interstellar medium internal gas of various galaxies at low and high redshift. Some of you may recognize some features here that may remind you, astronomers in the audience, of your stellar astrophysics course in graduate school. And low abundances, you see basically that the gas plateaus at low nitrogen abundance. This is what we call the primary production plateau. And this is basically primary production of nitrogen in more massive stars in the earlier parts of the universe. Then you also get secondary production of hydrogen at some later points in later generations of stars. And that's why at higher metallicity, you get this strong increasing trend of metallicity in terms of your nitrogen to alpha abundance. So here are the measurements from the CuPSat systems. It scales up to 100 kiloparsec away from galaxies. Different color points are again what you see looking at different clouds in the same kind of CGM of the same galaxy. And what you're looking at now again is a plot of relative abundance of nitrogen to alpha relative to metallicity, superimposed on what we see in the interstellar medium of gases of various masses. So let's go over one specific example. Our measurements here are shown in blue stars, each one marking individual clouds detected in the absorption complex, right? And you can see here both the overall gas metallicity as well as the nitrogen abundances are consistent with observed values in the H2 regions, interstellar medium of dwarf galaxies. So what do we know about the galaxy environment of this system? As it turns out, these are actually real data. It's kind of like an emission image of the system. And you see these are actually they're a close pair of dwarf galaxies, within only about 30 kiloparsec away from this background line of sight, shown in magenta. Our measurements here indicate that these galaxies have an interstellar metallicity of about 0.1 solar. So it matches with what you see in the gas. The most likely explanation we're looking at is that this gas, which has been stripped from the interstellar medium of one or both of these galaxies in the process of interacting. This is also corroborated by the fact that you do see disturbed morphologies in the images of these galaxies, which are again telltales of galaxy interactions. All right, we're getting close to the end here. I want to end with a taste of what we'll be able to do in the future. One of the things that was pointed out by the decadal survey was the need to start doing spatially resolved mapping of the CGM. One of the primary recommendations was a telescope that would allow absorption spectroscopy over a much higher density of background quasars, both in the UV and in the optical from the ground. So these are some of the concept images and some of the ongoing projects. And the hope is, instead of having to only get one background lens per galaxy, you can get and create a 3D absorption map of the CGM and study its spatial structures and spatial properties. So why is that important? Why is spatial properties important? I'll show you why. So this is a bit of a spherical cow kind of example, but you're physicists, so we know how to deal with spherical cows. So that's because traditionally quasar absorption spectroscopy of the CGM relies on single background lines of sight, like I showed earlier. So with this one-dimensional look, your direct kinematic knowledge is basically whether the gas is moving away from you or moving towards you, in which case it would be redshifted if moving away, or brushy it moves moving towards you. Without any additional spatial context, right, then you have a degeneracy here. Suppose there's a gas cloud which is outflowing in front of a galaxy. It's going to show you something that is blue shifted relative to the galaxy in absorption. What would happen to a gas cloud that is falling into a galaxy, but behind it? It would also appear as something that is blue shifted in your data. But this is a problem. It's a degeneracy. To break this degeneracy, we need to find a way to actually get spatial information, move from this pencil beam 1D approach towards higher spatial fidelity. We can actually resolve the CGM. And that's something that the next generation facilities like the Habitable Worlds Observatory, which we discuss a lot, and 30-meter class telescopes like the Magellan telescopes and the European extremely large telescopes will be able to do. With Hubble, normally have limit ourselves to quasars around the 18th magnitude. So in the far ultraviolet, or 19th if you're pushing it. That gets expensive very quickly. And there aren't very many of those UV bright quasars anyway. So the good rule of thumb is if you go and increase your sensitivity by half a magnitude, you double the amount of available background sources. So with a 6-meter glass in space, we shall be able to reach the 21st magnitude easily and increase for this nearby galaxy the amount of available lines of sight from just 1 or 2 to basically up to 30. 30-meter class telescope like the GMT from the ground would also be able to do the same 10 or more background lines of sight, but at a much higher redshift, probing in the earlier parts of the universe. So this is so exciting. But because we're going to have to wait a while for these things to actually come to fruition, we need to find something else to do. We can already emulate what we'll be able to do by doing CGM observations with multiple image lens quasar, which I kind of showed you a little bit. So lens quasars, that's GR, general relativity in action. This is what happens when light from a distant quasar at high redshift appears to be lensed by a massive object, like the massive elliptical galaxy I'm showing here. This lensing creates multiple images of the quasar on the sky. And this is what you see. 4 images of the same object. It's probably somewhere in reality behind that galaxy. You can really see it, but there are 4 images now. And this is why it's awesome. Gives you an ability to basically probe CGM of anything in the foreground, the quasar, at 4 different locations in this case. You kind of get a rough spatial mapping of what the CGM looks like around various galaxies. And finally, because of the way lensing geometry works, so you go to higher and higher redshifts and farther distances, you get to probe smaller and smaller physical separation because the visual emitting object, it's basically an accretion disk the size of like the solar system. So as you go to higher and higher redshift, you probe smaller and smaller still physical separation. We know about 300 lens quasars today. When I was starting in this field, we knew about 50. And right now, about 50 are bright enough to be observed in higher spatial resolution and spectral resolution with the current largest telescopes. One of the things I've spent a lot of time in the last few years is to build the largest spectroscopic sample of gravitational lens quasars. I have about 40 of them now, observed with the largest telescopes, and I've obtained really exquisite data, the best spectrographs in the world. With my collaborators, I'm now conducting a deep spectroscopic survey of these fields to identify and characterize foreground galaxies to study their CGM. Now, by the end of this decade, with new surveys like LSST, due to be online next year, it's projected that thousands more will be found, and most will be within reach of the next generation of telescope. So it's going to completely change the way we study the CGM from kind of 1D approaches to basically getting a real spatial mapping of the CGM while waiting for the real big guys to arrive maybe in 2040 or 2050, I don't even know. And so I want to end with a taste of what's to come. I'm showing you here the field around a lens quasar. And this image here is the Hubble imaging data, and you see it's a quad. So it's been imaged and formed 4 images on the sky. And I found this particular galaxy from archival data, redshift of about 1.6. So it's about 10 billion years ago. And so this is interesting. And I'm showing you here the absorption spectra for these 4 different quasars, A, B, C, and D, right? For magnesium-2 and iron-2, singly ionized magnesium and singly ionized iron. And in addition to these 4 lines of sight, right, I've also obtained actually and found self-absorption in the spectrum of this galaxy itself. So it's like because it's self-absorption, the light originated from the galaxy itself, and it's blue shifted, you can conclude very robustly that this galaxy is driving an outflow. Well, now let's look at these profiles together. They're complex kinematically, right? It's a whole mess. But even if with simple visual inspection, with that, you can already see some similarities kinematically between some pairs of lines of sight. For example, A and C are closer to the galaxy, and their profiles appear to be kinematically more complex, broader and more kinematic components. B and D, on the other hand, are further away, and comparatively speaking, you can see that the gas appears to be simpler in terms of kinematics. At the same time, the chemistry also appears to be different. It looks like there is a lot more iron in B, for example, than it is in D. And in A than perhaps in C. It looks like there's some spatial variations in the chemistry as well. Now, for example, based on the kinematics that we see here, and this is very preliminary, looks like we're looking at evidence of a wind, an outflow that is decelerating with increasing distance. And also it becomes less collimated, less ordered with increasing distance from this galaxy. We can also study the chemistry and how it varies spatially to learn more about the enrichment sources itself. I think this is one of the major ways that we are going to make much more progress in understanding the CGM from observational side in the near future. And it's going to be a synergy between spatially resolved maps of the CGM, spatially resolved chemistry, along with advances in theoretical modeling. And that's why people like me are here for the past month, 2 weeks or so. So we're now at the finish line. I've shown you that understanding the detailed physics of the CGM is going to be instrumental to solving open questions in the field of galaxy evolution. I hope I have convinced you that investigating the chemistry of the CGM provides us with a potent tool to establish a direct link between the CGM gas and their origins in individual galaxies. And finally, I hope you can share at least a bit of my excitement that spatially resolved observations of the CGM is going to be key completing our understanding the CGM and its role in galaxy evolution in the next decade and beyond. And with that, thanks again. It's been a great few weeks, and I'm happy to take your questions. Yes, Tom?
I found your observations of the different chemical composition of the active versus non-active galaxies quite interesting. How can you infer from these observations the cause-effect ratio? So, otherwise speaking, did they shut down star production because of evolving to a chemical composition, or did they evolve to a different chemical composition because of the stop of star production? Can you actually tell this apart?
Yeah, that is a very astute, and I think it's a great question. I think in order to because you're absolutely right, it's a correlation, right? It's a correlation, and causation is a different level of evidence. I think to answer your question, we have to kind of piece together different pieces of evidence, not just the chemistry, which again suggests that type 1a is more dominant at this point, and makes sense because these are dead galaxies; they haven't been forming stars. You wouldn't expect any young stellar kind of supernovae reaching the gas at that point. So everything that enriches the gas must have taken place after star formation has shut off. But to really answer the question as to why there's really stop forming stars, you can look into things like the kinematics of the gas and also the thermodynamics of the gas. And this is, of course, are ongoing in early stages of work. But we do see that in these massive elliptical galaxies, cool clouds, even if they do exist, they appear to be more disturbed and more turbulent. And this is something that I've been talking to my theoretical colleagues in the past couple of weeks. And we don't really know what the real answer is, but that might help answer why despite the fact that there's so much gas around them, somehow the gas doesn't really fall in and make new stars, because the amount of gas, you can calculate roughly the dynamical timescale for infall. And if you just do a quick division of the amount of gas divided by the amount of time it takes for infall, you arrive at some kind of expected star formation rate. And for this kind of galaxies, you would expect, at least a few to 10 solar masses per year, given their mass and dynamical timescales. We see less than 0.1 solar masses per year. So there's a huge difference there between the expectation and what we actually see. And this is why it's so important to figure out what's going on. And I think looking at the internal physics of the gas is going to be the key towards answering the question at some point, hopefully in the near future. Another question? I'm sorry, I don't know your name. Yes. Okay.
Wasn't there is all changes out on the like that series.
All right.
I'm not too sure if I understand well why quasar is coming to us in let's say 2 or 3 or 4 months. Why is not it's just geometry that, or is when if I have someone who's in behind that?
You're absolutely correct, because the quasar actually they reside in a host galaxy, right? It's not just an independent disk. So you're absolutely correct. Actually, the reason that you see it as only 4 images primarily is because the accretion disk, which is producing the quasar light, is significantly brighter than the host galaxy itself. The brightest quasars are 1,000 or even more brighter than the whole of the galaxy. So it's not that they're not there, but they just completely overshadowed by the light from these accretion disks. And in fact, if you do it really, really carefully, and I want to show you quickly here because this is really fascinating. And I love when people talk about details because I know I can talk about this for days and days, but I don't really want to bore you. But yeah, if you look at this, you can actually try to subtract the light from the quasars carefully by modeling the point spread function of the light, as we call it. And I did that, and I'm happy to show you. Once you get rid of the light from the quasar, you'll see basically a residual ring around this four, and that's actually light coming from the host galaxy of this quasar, which had been perfectly lensed to form a complete Einstein ring. Yes, exactly. But that's exactly how lensing works, and that was a very astute observation there. Yeah.
And the second question is a bit more general. In all these type of studies you are doing, first you said that one of the things we maybe have contact is with dark matter, okay? Okay, we're looking in the laboratories to make what's up and things, but okay. I'm wondering if this one is studying global beach at Baryon velocities, etc. You take into account that there may be also dark matter?
Yeah, we do. So I mean, well, yes. So absolutely correct. With lensing, right? The image separation here is going to be proportional to. It's going to be a function of the mass. It's going to be roughly the square root of the mass. So the larger the mass that is contained within, the larger the separation will be. We do have lenses for which the deflecting object is a cluster, and they can be really, really huge arc minutes on the sky, as opposed to just 1 or 2 arc seconds. And in fact, we do. People do include the effect of dark matter in the modeling of lenses themselves. But most of the time, when you're dealing with individual objects, we do know that the dark matter only becomes dominant at large distances from galaxies, and close to galaxies at only a few kiloparsec away, the baryonic matter is still dominant.
So you can, my question was, you cannot, from this study, get some idea of the dark matter distribution or movement or whatever.
I think you wouldn't want to look at this kind of like small scale galaxy lenses. There are people who actually studies lensing around clusters for which the dark matter may be probably dominant in the mass distribution, and they can actually obtain some constraints, albeit indirectly. I think in terms of direct detection of dark matter, I would really rely on you guys, the particle physicists in the audience, to tell us what it is and what the masses are and whether it's interacting or not interacting. And yeah, so let's converge again in a few years and tell us what you have found. Thank you. Thank you so much.